Hey, what's up guys? Day 3, so quadratics refresher. Why Model 1 uses the delta temperature squared. Alright, let's see what we got here. For our AI created lesson, goal, see why a simple line isn't enough, how a quadratic model bends to match real building behavior in cold climates with heavy envelopes. Warm-up time does not increase linearly as the delta temp gets larger. Model 1 introduces quadratic term to capture this curvature. Why quadratic shows up in HVAC system warm-ups. When the delta temperature is small, like 2 to 3 degrees, the building warms almost linearly, but as the delta temperature grows 8 to 12 degrees, like if it's really cold outside and the zone temps drift 12 degrees, I think they're saying every extra degree tends to be more minutes than the one before. Coil capacity is fixed and maybe maxed out. Heat transfer slows as the temperature approaches discharge air temperature. Envelope losses increase with larger temperature delta. A quadratic model allows the slope to increase with delta temperature. So here we go. Minutes equals A times delta T squared plus B. A controls how quickly minutes per degree grow, and B remains the baseline overhead. This is exactly PNNL's Model 1 structure. So consider the model with the variable A equals 0.5 and B equals 4. So this would be the intercept variable we were talking about in the last video, where it's just the lag, I think. Okay, so delta temperature 2 degrees, the building sat overnight. 4 degrees, 8 degrees, the building sat overnight. If it got really cold, I'm seeing 10 or 12 degrees currently in Wisconsin right now because it's getting pretty cold. So delta temperature squared, so we're just squaring these two values, squared, and here we go. So a variable times 4 times 16 times 64, which is our value here, plus our intercept value. So this is our calculated warm-up time from the math model. And as you can see, it's not linear. It doesn't go 6, 12, 18. It goes 6, 12, 36, which could make sense in the real world application. See how doubling the delta temperature from 4 to 8 more than doubles predicted time? Yes, to the curvature we need to accuracy. Okay, solve a quadratic model by hand, which I'll do in Python because I'm too lazy to draw up by hand. Okay, so here's our data. This is what we see. So you assume, okay, so pick 2 rows to solve A and B. So they're using this row of data and then that row of data. So they're solving the rate first, which would be the degree per minute calculation, I think. So that would be, yeah, so this is minutes, and then this is degrees squared. So then here is the quadratic warm-up model. Alright, so here's our micro exercise for today. Okay, here we go. So I'm just going to take this little cheat sheet here. So Python warmed up. What was our we have to get our data. I'm just going to copy this again. Actually, they're giving us the equation, so we don't even have to do any of this stuff. So I'm just going to copy this. Okay, so this was our delta temps. So maybe I could just do, I'm gonna have to rewrite this. So we have a 3, 5, and 7. 3, 5, 7. So I'm just gonna make this like delta temps. Then in Python we can make this into a list or an array. So then we could even loop through this. We could do for delta t in delta temps print delta t. Python math lesson. Okay, so then we can print all this, and then we could probably even make this into a function in Python, which might be a little handy. Okay, so this would be basically, what could we name this? Maybe we could just say function. You do in Python, you create a function called def, and we could just name it compute times. And then we could just say we'd have to pass in the parameter for A and B, I think. And basically, we would have this little function here. Below it, let's see. So I have to think about this a little bit. So quadratic model. And I want to return t. Alright, so A and B. Let's see, did we have to compute? I think we just plug it into the equation. So so this is basically our, I think, sorry, this is wrong. This would be our delta temp. And we're going to just say delta temp like that. And then this would be like returning minutes. So t is minutes. I kind of like using the word minutes. It makes more sense to me. So minutes. Alright, so they gave us 0.7 and 6, which we have in here in our equation, and then we just have to feed the values into our function. Okay, we could even wrap this in a print statement. Alright, so I'm gonna comment this guy out. So this would be, we could say minutes Alright, so this is the minutes we have getting calculated here. If we really wanted to get fancy, we could even round. Python has a built-in function called round to the nearest hundredth. Alright, so that's looking kind of nice. It doesn't really look like it's a super big curve here. But unless I'm doing something wrong. Am I doing something wrong? Okay, actually I think we forgot to square this. Okay, that looks a little better. Yeah, there we go. We forgot to use the forgot to square it. Okay, so this looks a little better. So we have minutes there, and you can kind of see in the data, it's definitely would be a curve. Another thing that might be kind of fun is to actually plot this. So we could do something like this: data for plot equals a list. And there's actually a plotting library called matplotlib.pyplot, which is just a basic plotting library. So like we could even, so what I'm going to try and do right now is append this minute data to an empty list. So in Python, which is kind of nice, you could just do data for plot dot append what we could even do here is call the function ahead of time, so we could do data equals that. So we're calling the function on the for loop. We could put the data inside the list, and then also print it. And then at the end, when the for loop is done, we can even print this as well. So I'm just going to print. Oh, okay, so no, we don't have this installed. I'm just going to Google this real quick. Pip install matplotlib Python. Alright, so if you're on Windows, so here we go. This is just to install the plotting library. You just do Python-m pip install matplotlib. So it's installing this couple Python packages here with pip, the Python package manager. This might be kind of fun to play around with later on, and we could do some plotting too. So if we want to do, all right, so it looks like it's done. Oh shoot. Run the script. All right, so then as we can see here, that works nice. These are our modeled minutes, and that's getting saved to our data structure here, which is just a list. And then we're computing the data with a little function here, returning the rounded calculated minutes, and then actually adding that data to just a blank list in Python, printing it, and then printing here, we're just verifying that is plotting. So if we want to actually plot this, I think we can just do plt.plot. So we could just sorry, 1 second, I'm trying to, you can just do plt.plot. Then this would be our data for plot, and the plt.show, I think. See what this does. Ooh, and we got a little plot here. So it doesn't have any data to show on the X or Y axis, or you can make these really fancy. But this would be to kind of just show, like, it's not perfectly linear. It's not exactly straight. It's made up data for one thing, but in the real world, it would have like a little bit of a curve to a quadratic function, which makes sense. As the building gets colder, it's going to take more minutes for it to warm up. It's heat transfer theory in physics. So in a nutshell, we could plot this. Maybe we'll play around with that later on. So I think this is it for day 3 on the lunch break mini lessons. Let's see. So think practically. Does your building warm up linearly or quadratically for large delta T? So we already kind of answered that. So quadratic models capture the reality that warm-ups slow down as delta T grows. We've solved using exactly the same algebra as a line, but with this to the second power, this quadratic feature. So this is what PNNL Model 1 is. It's simply this quadratic form with coefficients that's learned from field data. All right, so that's all we got for day 3, and I'll try and do day 4 tomorrow. Thanks for watching.